Now we're thinking about energy in an oscillating system, and to do that, we need to recall a bunch of the ideas that we saw in 2201, the energy ideas. Energy is a property of a system. A system is just some set of interacting objects. And one of the interesting numbers is the total energy in the system, and that can be made up of different types of energy. The four that we focused on in 2201 and the same four that we'll focus on in here are kinetic energy, energy that an object has because it's in motion. Here's the rule for calculating kinetic energy: 1/2 mass speed squared. So of course, anytime an object has speed, it has kinetic energy. Gravitational potential energy, which is energy that an object has because it's interacting with the gravitational force from the Earth, and the amount of potential energy increases as you move that object farther away from the center of the Earth. The rule is mass times g times elevation. You define some zero level of elevation, and then at any non-zero elevation above or below that, you've got some gravitational potential energy. Then there's elastic potential energy, energy that an elastic object has because it's stretched or squeezed or twisted or bent or distorted in some way. Because any time you stretch or squeeze that object, you are actually giving it some energy that it didn't have before. We'll look at that in detail in a minute. And that energy that it now has, that it didn't have before, is stored up as elastic potential energy. The simplest elastic object that we consider is a spring that you could stretch or squeeze. And for that, the elastic energy is 1/2 K. This is the same K that appears in the rule for a spring force. There's our rule for a spring force. And then this is the size of the displacement away from equilibrium, or what amounts to the same thing, the displacement of the free movable end of the spring. We think of one end of the spring as fixed, attached to a wall, doesn't move. This end of the spring can either move this way when the spring is stretched or this way when the spring is squeezed. And then the displacement of that point away from equilibrium is what delta x means. So the more you stretch the spring, right, the greater the displacement of the movable end, so the more energy you're giving to the spring. And likewise, the more you push the spring, the more you're displacing the right end of the free end of the spring away from equilibrium. So again, you're giving it more energy in that case. So when thinking about a system, the first thing to think about is what objects should be in that system. The object is to choose the objects so that under as many different circumstances as possible, the total energy of the system stays constant. And remember, back in 2201, there were 4 rules, and if you followed those rules, then much more often than not, the total energy of the system would stay constant. 3 of those rules are still relevant here in 2202. all moving objects have to be included in the system. All moving objects, since they have some velocity, they'll have some kinetic energy, and that energy has to be taken into account. So include all moving objects. And if there are any elastic objects that get squeezed or stretched or distorted in some way, they must be included, because when they are getting squeezed or stretched or distorted, they're getting some elastic potential energy. And you have to take that energy into account. The third rule that we need to remember, any object that is the source of a friction force must be included in the system, because whenever there is friction, friction will actually result in taking energy away from the thing that feels the friction force. And where does that energy go? It doesn't just disappear. The energy goes into the thermal energy of the system. Remember, thermal energy is just the grand total kinetic plus potential energy of the molecules that make up all the objects in the system. So those are the basics. One other thing that we do think about here, we didn't need to think about it in 2201. We think about all the kinetic plus potential energy as sometimes as one type of energy called mechanical energy. We lump those two things together because very, very often energy is transformed from kinetic to potential and back to kinetic and then back to potential. That happens all the time when an object is oscillating, which we'll see in shortly. Okay, energy is a property of a system. How does a system get energy in the first place? It gets energy, or how does a system lose energy? It gains energy or it loses energy by the process called work. Work, as you remember from 2201, happens whenever a force acts on a moving object. So, and the numerical value of the work tells you how much energy is gained or taken away from the object that is feeling that force, from the object that is having work done to it. The rule for calculating that amount of work, that amount of energy, is a magnitude of a force, a magnitude of a displacement, cosine of an angle. So for instance, some object starts at an initial location here and travels for a little while and ends up at a final location there. The displacement vector would be just that. And the magnitude of that displacement vector is one of the factors in the work equation. And while it's moving, while it's getting displaced, it feels a force. And let's say the force is pointing in this direction. And so there's a magnitude of that force. And then the angle there is the angle between the displacement direction and the force direction. So it would be this angle in this particular example. One thing to notice, this is a magnitude or a size or an absolute value, which means it must be positive. This too is a magnitude, a size, an absolute value, so it must be positive. This could be either positive or negative or zero. In other words, determining whether the work done is positive or negative is entirely a matter of this cosine factor. Okay. So, basic idea. Positive value for work means that much energy is given. Given to the object that is feeling this force, given to the object that's moving through this displacement. And then negative value for work means energy is taken away from that object. So whenever we talk about a system gaining energy or a system losing energy, what we're really talking about, to be more precise, is that one piece of that system, one object within that system, is either having positive work done to it or having negative work done to it. But let's consider two cases. Let's say, here's our system, and in that system, a whole bunch of objects, and there's two of them, thing one and thing two. And let's say, while thing two is moving, it feels a force from thing one. Force from one on two. And since 2 is moving while it feels that force, work is done. And let's say that that work is positive work. The work on thing 2, positive work. In other words, thing 2 gained some energy by having work done on it. Well, energy doesn't appear out of nowhere. That energy that thing 2 gained had to come from somewhere. It came from thing 1. Because, think back to Newton's third law, if there's a force from thing 1 on thing 2, then there's an equally strong force in the opposite direction from thing 2 on thing 1. From thing 2 on thing 1. And it turns out that because that force is in the opposite direction from the force that did this work, this force will do work that is opposite in sign, has the opposite sign from the work done by this force. So in other words, the work done on thing 1 is negative. That is, energy is taken away from thing 1 when this force does work on it. So now we see where, when thing 2 gained energy, now we see where the energy came from. Energy was taken from thing 1, given to thing 2. But thing 1 and thing 2 are within the system, so when that energy is transferred from thing 1 to thing 2, the total energy of the system does not change, because when the energy moved from thing 1 to 2, it started out inside the system and it ends up still inside the system. So for this case, change in the system's energy is no change. And that's what happens whenever any internal force does work. And by internal force, we just mean forces like these, forces that have one part of the system as their source and another part of the system feeling that that force. Right? The internal force is an interaction entirely inside the system, and it can do work. It can move energy from one part of the system to another part of the system by means of work, but it doesn't change the grand total energy of the system. On the other hand, imagine an external force. So there's our system. Thing 2 is still inside the system, but now we'll imagine something that we'll call thing 1 outside the system. But we'll imagine that thing 1 is still applying a force to thing 2. There's the force from 1 on 2. And thing 2 is moving while it feels this force, so work is done on thing 2. And again, we'll say that that work turns out to be positive, which means thing 2 gains energy that it didn't have before. But same thing happens. Since this force is present, then Newton's third law tells us that there's an equally strong force in the opposite direction from thing 2 back on thing 1. From thing 2 on thing 1. And so that force will do work on thing 1, and because this force is in the opposite direction from this force, the sign of this force's work will be opposite to the sign of this force's work. So one has negative work done on it. So now something different is happening from what happened in this case. Now, it's still the case that energy is being moved from thing 1 to thing 2, but that means that energy is being moved from something outside the system and being given to something inside the system. In other words, the total energy of the system now has increased. And that's so there is a change in the total energy of the system when work is done by external forces. In other words, whenever we're talking about the energy of a system, one important question to answer is there work done by any external forces? And to do that, you first have to see what forces are there in the first place, and then decide whether those forces are internal or external. Then look at the external forces and see if any of them do any work. If that happens, then the total energy of the system would change. Here's a simple example of that using our model for an oscillating system, the spring mass model. So the the simplest version of that model, just a horizontal spring attached to a mass. The mass can oscillate back and forth, left and right, and it's oscillating, it slides along a very, very, very smooth surface so that we can say there's essentially no friction. So, first question, but then the mass starts out at the equilibrium point, and then I pull the mass to the right. So the initial location of the mass is there, the final location of the mass is there. So there was a displacement of the mass and also a displacement of the movable end of the spring. Now, while that process was happening, what forces were present? Were they internal or external? Did they do any work? Well, to figure out whether a force is internal or external, you have to know what things are actually inside the system. So use those rules I mentioned before to figure out what is inside the system. Anything moving has to be included in the system, and the mass moves. So that's part of the system. And any elastic object that gets stretched or squeezed has to be part of the system, and the spring is getting stretched, so that'll be part of the system. And if there's any object that is the source of a friction force, that would be included in the system as well. If there were any friction, then this surface across which the mass slides would have to be included, because that surface would be the source of a friction force on the mass. But there is no friction, so these are the only two pieces of the system. So next, what forces are there? Are they internal or external? While I'm moving the mass, there are four forces. There's the weight, of course, and then a normal force from the surface pushing up, and then the spring force, which always points opposite to the displacement. I'm moving the spring to the right, so there's a displacement to the right, which means spring force is pulling to the left. And there's, of course, the force from my hand pulling to the right. And strictly speaking, it's a static friction force. I'm able to pull it to the right because my fingertips are sort of stuck to particular points on the block, and the block doesn't slip out of my hands, but instead is pulled right along with my hands. But we'll just call that a pulling force, even though it's really static friction. Okay, so what forces are internal, what forces are external? Well, this force comes from the spring, which is part of the system, so it's internal. This comes from the surface, which is not part of the system, so it's external. Likewise, this force comes from the earth, so it's also external. And this force comes from my hand, which is not part of the system either, so it's also external. Three external forces. Do any of those forces do any work? Well, If they did, then the energy of the system is going to change. Remember our rule for work and apply it to the weight force. The work done by weight is equal to the magnitude of the weight force, m times g, times the magnitude of the displacement, which is just the absolute value of delta x, times cosine of the angle between displacement and force. But the displacement, remember, was horizontal to the right, and the weight force always points straight down. So the angle between displacement and force is 90 degrees. So this term here is cosine of 90 degrees. Cosine of 90 degrees turns out to be 0. So the work, this is an external force, but it does no work. And for exactly the same reason, this external force, the normal force, will also do no work. Work done by the normal force is just the magnitude of the normal force times the magnitude or absolute value of the displacement times cosine of the angle between the displacement and the force. The force is vertical, the displacement is horizontal, so the angle between them is 90 degrees. And again, you've got cosine of 90 degrees, which comes out to 0 again. So two of those external forces do no work. This one, however, does do work. It'll be positive work. In other words, this force doing work will give energy to the mass spring system. Work done by my pulling force is just the magnitude or the absolute value of that pulling force, the absolute value of the displacement times cosine of the angle between force and displacement. Force points horizontally straight to the right, but the displacement was also horizontal, straight to the right. So the angle between displacement and force is no angle at all, 0. So we've got cosine of 0 degrees. Cosine of 0 degrees turns out to be positive 1. Positive work is done on the system by my pulling force. And that's work done by an external force, which means energy came from outside the system and was given to the system. So in this case, the work done by external force is positive. One thing to be careful of, whenever I use this W with no subscripts at all, this will always mean the grand total work, the net work done by all the external forces, or what amounts to the same thing, the work done by the net external force. Add up all the external forces to see what the net external force is, and the net, and if that net force does work, then the system's energy changes. In this case, the work is positive, so energy was given total energy of the system increased? Well, specifically, what parts of the system's total energy increased? Whenever there is an energy change, it could come from a change in one or more of the different types of energy. Maybe a change in kinetic, or a change in gravitational potential, or a change in elastic potential, or a change in thermal energy. So that was a positive change. This is zero because at the start the mass was just sitting there at the equilibrium position, and when I finished moving it, it had come to a stop again. So at the beginning it started with zero speed and therefore zero kinetic energy, and then I pulled it and at the end it stopped. So again it had zero speed, so again zero kinetic energy. So the kinetic energy at the beginning and end is the same, zero. So there was no change in the kinetic energy, no change in the gravitational potential energy because everything happened horizontally. That is, the elevation did not change. Gravitational potential energy is mass times g times elevation. Obviously, those factors did not change, and elevation did not change either, so there was no difference between the initial and final gravitational potential energies. However, there was a change between the initial and final elastic potential energies. The spring started out unstretched. The spring ended up with some stretch. So in other words, in the initial state when the spring was not stretched, the right-hand end of the spring had a displacement of zero. It was right at the equilibrium position. But after the spring had been stretched, this number was not zero. So the spring now had elastic potential energy that it did not have before. And then thermal energy, well, a system gets thermal energy by means of work done by friction. Work done by friction takes energy away from moving things and gives that energy to the system's thermal energy. But there is no friction in this case, so there is no work done by friction. So that kind of energy transfer can't happen. So there's no change in the thermal energy in this case. So that means that I gave the system energy, and when I was finished doing the work that gave the system energy, all that energy I had given to it shows up as elastic potential energy. Now let's look at that same system immediately after I let go of the mass. So here's the wall, there's the equilibrium point, and there's the mass, and at the instant I let go, it has zero velocity, but it starts to pick up velocity to the left. There's the initial location at the beginning of this process that we're now thinking about, and at the beginning of that process, the speed is zero, and then the process that we're considering starts when the mass is way over here after I've finished pulling it and now I let go. And the process that we're considering will end when the mass has returned to equilibrium. But of course, when it returns to equilibrium, remember, it's been speeding up all the time as it approaches equilibrium. Right? It's moving to the left, but it's feeling a restoring force which always points toward equilibrium. In other words, it's moving to the left and simultaneously being pulled to the left by the restoring force. So anything that feels a force pulling in the direction where it's already moving is going to speed up. It speeds up all the time until it gets here. So here at equilibrium, the final location is the equilibrium location, and the final velocity is the maximum, or the final speed is maximum. It's been speeding up all the time as it approached equilibrium. So now let's go through the same process. There's some differences between what we saw before. In this case, now the pulling force from my hand is no longer there. The pulling force from my hand is no longer there. That was the only external force that did work. So since that force is gone, there is no work done by external forces. The two external forces that remain, weight and normal force, both do zero work. So, since no work is done by external forces, the system's energy does not change. System's energy stays constant. But think about energy changes of the individual types of energy here. The kinetic energy increases because at the start of this process, there's no speed, so no kinetic energy. At the end of this process, there is speed, so there is kinetic energy. An increase, a positive change in the kinetic energy. And just like before, everything happens horizontally, so there's no change in elevation, so there's no change in gravitational potential. There is a change in the elastic potential energy. In the initial state, the spring was stretched, so it had potential energy. In the final state, the spring is not stretched at all. It's at its normal equilibrium shape, its equilibrium location. The free end of the spring is right at equilibrium. So there's no displacement of that free end away from equilibrium at all. So there's no more elastic potential energy. All that elastic potential energy has gone away. In other words, a negative change. The spring lost elastic potential energy. And since there's, again, no friction to worry about, there's no process by which the thermal energy can be increased. So now, what have we got for this equation? To see what this equation really means, let's write it out in complete detail. Delta E is 0, and then we have to include only the non-zero terms on the right-hand side, so that's delta K plus delta elastic potential energy. And whenever I say write out this equation in detail, what I mean is this. Delta anything is the final value minus the initial value, so write that out in detail in terms of masses and speeds. 1/2 mass final speed squared minus 1/2 mass initial speed squared. Final minus initial kinetic energy. And then similarly, write out the change in elastic potential energy in detail. Write it out in terms of the K's and the displacements. So 1/2, whatever the K value of that spring is, times the final displacement squared, the displacement when the system gets to the final state, minus 1/2 K times the initial displacement squared. Whatever the displacement was at the very beginning of the process. Okay, so those are the only terms that are interesting at all, but we can simplify because in the initial state the speed was 0. So that factor is 0, so this whole term is 0. And likewise, in the final state, the spring is back to its equilibrium length. It is no longer stretched or squeezed. There is no displacement away from equilibrium, so final displacement is 0. So that term goes away. And then the equation comes down to just two things. 0 equals 1/2 mass final velocity squared, but let's call that the final velocity happens when the mass is at equilibrium. This is the velocity at equilibrium. In other words, this is the velocity at equilibrium, which is the highest velocity that it achieves. So we'll call it that. The velocity when the oscillating object gets back to equilibrium is the maximum, or has the maximum speed. Minus 1/2 K initial displacement. Well, the initial displacement turns out to define the amplitude of an oscillation. Whatever the initial displacement is, that will be the amplitude of the oscillation. We'll look at that in more detail in class. But that means we can write the initial displacement as amplitude. So that's all we have. So simplify that a little bit. Just add 1/2 Ka squared to both sides of the equation, and then we have 1/2 K amplitude squared equals 1/2 M maximum speed squared. There's a factor of 1/2 on both sides, so I can cancel out. And then I'll divide both sides of the equation by M. So I have K over M times amplitude squared equals maximum velocity squared. Make it even simpler by taking the square root of that whole equation. So the square root of K over M, square root of A squared is just A. Square root of Vmax squared is just Vmax. So now we have a direct proportionality. Vmax is just constant factors times the other variable, amplitude. In other words, maximum speed is directly proportional to the amplitude. If I pulled the mass back twice as far, I would have given the oscillation twice as much amplitude, and that would mean that the maximum speed achieved at equilibrium would be twice as fast. One last thing to think about here. Let's consider the same process, starting out from 0 velocity and then the the mass moves back towards equilibrium while it's speeding up. So there's the mass in its initial state, and its initial, like I just said, its initial displacement away from equilibrium is A meters, A for amplitude. And as soon as I let go, the process starts. So the initial location is just A, the initial velocity is 0. So what's the total energy at that moment? Well, total energy is kinetic, but there is no speed, so there is no kinetic energy. Everything happens on the same elevation, and I am free to define that elevation as 0. So if you're at the 0 level of elevation, you've got 0 gravitational potential energy. The spring is stretched, so we do have some elastic potential energy. 1/2 K times the square of the amount of stretching. And then the molecules and atoms inside the spring and mass do have some kinetic and potential energy, so there is thermal energy in the system. But remember, we divide the energy, the total energy of a system, into mechanical energy and non-mechanical energy. So at this moment, the mechanical energy, which is all of the kinetic plus potential, which is all of this, is simply 1/2 K times amplitude squared. Now, remember, for this case, since my pulling force is no longer there are no longer any external forces doing work. No work is done by external forces, so there is no change in the system's total energy. In other words, the system's total energy stays constant. That sum stays constant. And since there's no friction in this case, there's no way to gain thermal energy, so that stays constant as well. So the sum is constant, that term is constant, so that term is constant. Or in other words, the mechanical energy always has this value. And at other points in the oscillation, there can be less potential energy and more kinetic energy, but that sum of kinetic plus potential, in other words, the mechanical energy, will always be equal to this number. So in other words, the mechanical energy is constant, and you could calculate it that way. But what do we have here? We have another direct proportionality. We have mechanical energy equals constant factors, 1/2 K, times a variable, A squared. In other words, mechanical energy is directly proportional to A squared. However, A squared changes mechanical energy changes the same way. And this relationship between amplitude and mechanical energy turns out to be a very important relationship. We'll be thinking about that a great deal in the upcoming classes.